Hello, welcome back. What's shaking, everyone? We are doing day 2 of our biopsych unit review of unit 2. Yesterday we talked about the parts of the brain, and now we're gonna break it up into the building blocks of the brain. So talking about the nervous system, neurons or communicators, neurotransmitters, and drugs. So let's get started. So overall, there's kind of two main systems of how our body communicates. The one that we talk about most in AP Psych is the nervous system, because that's made up of the neurons that communicate in our brain. And then we have the endocrine system, which is our hormone system. We don't talk about that one as much, but I'm going to go over real quickly the main things that we do need to know about the endocrine system, and then spend the rest of our time talking about the nervous system and neurons. So, endocrine system, again, just know that it's our body's chemical messenger system. And then the way that it communicates, just like the nervous system communicates with neurons, the endocrine system communicates with hormones. So it releases different hormones into our body. There's a bunch of different glands, like the pineal gland that we said that kind of controls our circadian rhythms by releasing the hormone melatonin. The main gland, though, that we need to know is the pituitary gland, and that's because it's the master gland. It's the head honcho gland that kind of controls the entire endocrine system and is responsible for telling the other glands to secrete certain hormones to kind of regulate our body. And then, best thing to know with the endocrine system is that it's very attached and connected to that hypothalamus, because the hypothalamus is the one that's checking the temperatures, making sure that our body's at equilibrium and homeostasis. So the pituitary gland, like I said yesterday, works in conjunction with the hypothalamus to make sure that everything's balanced and communicate and tell the pituitary gland to start having hormones being secreted to help regulate the body. And one other important part of our endocrine system that I wanted to bring up, in addition to the pituitary gland, is the adrenal glands. And these have come up a couple of times on AP FRQs, so I wanted to mention that they're important. And the main reason why they're important is because they're connected with our fight or flight response. So how they are connected with that is that the adrenal glands are just a pair of endocrine glands that are located above the kidneys. And the reason they're connected with the fight or flight response is because they secrete the hormones epinephrine and norepinephrine. And I'm going to talk about at the end of the video how norepinephrine plays a role in kind of helping us begin that fight or flight response by helping us get aroused and get that kind of energy to increase our heart rate and flee the situation. So adrenal glands, you can kind of think adrenaline and that rush to be able to run and flee in the fight or flight response, tied in with that, with your autonomic nervous system and the sympathetic nervous system. So enough of that. Now let's get into the nervous system. So we know the nervous system is made up of two divisions. There's a whole lot of smaller divisions that we're going to break down in a sec. But the two main divisions of the nervous system are the central nervous system and the peripheral nervous system. And you can see here in green, the central nervous system is the one that just contains our brain and spinal cord. So main thing, brain, spinal cord. And then peripheral, you can think if something's on the periphery, it's on the outskirts. Peripheral is everything coming off of our spinal cord. So anything that kind of would be more movement, voluntary movement, that is the peripheral nervous system. Obviously, central nervous system is our vital life functions because it's the brain and spinal cord. If we sever our spinal cord, you'd be paralyzed. It's kind of very vital. So we don't need to break down central nervous system anymore because we know it's just the brain and spinal cord. But then peripheral nervous system is the one that has a whole lot of divisions. So remember, you can think periphery, it's the stuff, the outskirts going off of the spinal cord. Then the two divisions below periphery would be the somatic nervous system and the autonomic nervous system. And when we talk about the neuron, remember we said soma means body. Like soma is the cell body. So somatic nervous system is controlling your body. It's the voluntary movements. So it's things like moving your arm, moving your legs. So if you had an FRQ question asking you how you might use the somatic nervous system to do something, you can answer by saying, oh, Susie might use her somatic nervous system in her big baseball game by, using it to hit the ball or something like that. So somatic nervous system is your voluntary movements of your body, soma. And then autonomic, that's super easy to remember. Autonomic, automatic. It's involuntary. It's kind of like your heart rate, breathing, all those things that you don't think about and consciously do. It's your body doing it for you. So then within the autonomic is our kind of fight or flight system. So when you think autonomic, think fight or flight response. That's the big thing that's associated with autonomic. And we know that our fight or flight response is something that we can't help. When we're scared, when we're fearful, that fear response just overcomes you. It's not something that you're willingly doing. Your body, you have a fear reaction, just jolt, and you can't help it. So within the autonomic nervous system is the sympathetic and the parasympathetic. So when you have your fight or flight response and something boo jumps out, scares you, your sympathetic nervous system is what's first activated. So that's the gas pedal. Sympathetic is the gas pedal turning on your fight or flight response. So what we see here is it's going to arouse your body and alert your body and start dilating your pupils, accelerating your heartbeat, increasing your breathing. It inhibits or stops digestion to kind of conserve that energy and redirect it so you can expend that energy by running and increasing your heart rate and things like that. We also know things like norepinephrine is a really good neurotransmitter we're going to talk about later that's connected with our sympathetic nervous system in the fight or flight response. And this helps us kind of gain that momentum to run away from something. So sympathetic turns the gas on. And then once everything's cool, we're not scared anymore, we averted the scary situation, then the parasympathetic, second thing that happens, parasympathetic nervous system takes over. And I think of parasympathetic, I remember it because it's like a parachute slowly calming you down and helping you to the ground. So parasympathetic parachute, and it's the brake. It's going to restore things back to normal. So when the parasympathetic nervous system is activated, it contracts your pupil, it slows your heart rate, slows your breathing, starts stimulating digestion again, so bringing things back to normal. Okay, and then divisions, I forgot to mention divisions within the somatic nervous system. There's two types of neurons that we need to know, and these are important ones to know. We have afferent and efferent, or sensory and motor. They kind of have same names, or different names, same function. So afferent, I remember because I think of access. So afferent is the kind of sensory neurons in that you're picking up sensations. So you touch something and then it's going to go up to your brain. Afferent access, or you can think sensory, right? Sensations, touching things, going into your body up to your brain. Efferent or motor, I think efferent exit. So you're telling your body to do something. So in your brain, you're thinking, I want to throw a ball. So efferent, it's going to go down here to your arm, exit, you're throwing the ball. Or motor, you can think movement. You're telling your body to move. Motor movement, willingly, consciously telling your body to move. So those are the divisions within there, and trying to put some kind of mnemonics or helpful ways to remember that. So how does our brain tell our body what to do? And that is through, like I just talked about here, the neuron. The neuron is just our little communicators that kind of work in a domino effect of communicating throughout the different parts of the brain and our body. They're what help get things from our brain down through our spinal cord and then to the rest of our body. So let's break down the different parts of the neuron. We know that neurons, again, specialize cells to receive, process, and transmit information to other cells. So just remember, neurons are your communicators. And it wouldn't be a true review of the neuron without our neuron dance. So get ready. You guys can go make your own TikToks of this or whatever. So you got dendrites first, nucleus, soma, axon, terminal branch, terminal buttons, synapse. So get ready. So just to breeze through this, typically AP, I've noticed on FRQs doesn't ask too much in depth about the neuron, but just to be prepared for anything. We know that dendrites, you can think they're just the ones reaching out, like Neil Diamond, reaching out, and they look like little trees or little hands kind of reaching out. So dendrites are the things that reach out and pick up the communication in their little branches. Then they go on to the cell body or soma and the nucleus, which is kind of the genetic hub that contains all the DNA information. Then once they pass that, it goes through the axon. And the axon is the really important part to know when we're talking about that whole action potential, because that's where everything's going down. So axon is the long branch, and it's also where all the action potential and things are going on with the movement of ions. So its job is just the branch that carries the message now to the terminal branch. And then we know that the axon is covered by the fatty layer of myelin sheath. So the myelin sheath, we know, is just something that's protecting and insulating the axon, and it helps increase the speed of transmission of the message. And we know that without it, if you have the breakdown of the myelin sheath, that's when MS or multiple sclerosis could happen. That's typically more of a multiple choice question that AP likes to ask, but maybe, you never know. So then after the axon, it gets sent to the terminal branch, and then those get ready to kind of alert the terminal buttons. And the terminal buttons are the little things that hold the neurotransmitters. So little things here. And then these contain neurotransmitters, which are the things that are kind of the keys that help us unlock and open up the next neuron, the dendrites of the next neuron, to keep sending the message along in that domino effect. So neurotransmitters are, again, just the key that's opening the lock on the next neuron. So then the neurotransmitters now have been released from the terminal buttons, and they have to cross the synapse, this little tiny gap. Sometimes it's called the synaptic cleft, the synaptic gap, just the synapse. They have a million different ways of referring to it, but it's all the same thing. So neurotransmitters have to cross the teeny little gap to get to the next dendrite of the next neuron. And we said that this synaptic transmission, the neurotransmitters are not the thing that's getting sent on and on through a bunch of different neurons. They're just the keys that open up the door to continue sending that neural impulse. So we already hit on this. So now let's get into kind of the electrochemical kind of neural impulse that causes the action potential, which allows you to keep moving on that impulse to the next neuron. So neuron, I think of it as a battery. This is because a battery, when it's just chilling, like you don't have it in a remote or anything, it's just chilling with the potential to release energy. But at that moment, it's not doing anything. It's just sitting there. But at any moment, if you put it into a remote, then it could be activated. So at resting potential, it has the ability to become active, but it's currently just chilling in a neutral state. So at resting potential, we know that the neuron has a negative charge on the inside and its axon. So when it's just chilling at resting potential, it's at a negative 70 millivolts. And this, on the inside, we said it's potassium ions and more negative proteins, which result in the overall negative charge. On the outside, there's positive sodium ions chilling. So now we're going to reference back to this picture. We have right here, this is resting potential at negative 70. So now we're going to see what happens when we have an action potential. So when the action potential happens, this is when the neuron starts to shift from negative to positive. It starts to depolarize. So when the neuron is just chilling at resting potential, it is polarized, which just means it's negative. So now it's going to begin depolarizing, and the action potential happens, causing those positive ions to flood and open the gates and move into the axon and make it an overall positive charge. So if we look back on our chart, this is depolarization. So it's going from overall negative to now positive and going and increasing till we have a peak. So it goes all the way up through 0, and it can even get up to a positive 30. So it's depolarizing, becoming positive. So then what happens is we have this thing called the all or none law. And this is saying that in order for a neuron to fire, and what we mean by fire is just pass on keep passing on that neural impulse and fire down the axon and move it on to the next neuron. In order for it to do this and fire, it needs to reach the threshold. So just the level of stimulation required to trigger the neural impulse. It needs to reach the threshold of negative 55. So we see here, this is negative 55. So it has to be strong enough impulse to reach negative 55. Once it does, it's going to fire. If it doesn't reach it, if it reaches like, let's say like negative 60 or something, it won't fire. It has to reach the negative 55 or else it's a lost cause. But what we do know is that once it does hit this negative 55, it's always going to fire at the same intensity, no matter what. So it could be at, negative 30. It could be at negative 50. It could be at negative 55. It doesn't matter. It's always going to fire with the same level of force and intensity. That is what the all or none hypothesis says. It says that it must hit the threshold of negative 55 in order to fire. And once it hits that, it doesn't matter if it's any greater intensity, it's always going to fire with the same intensity. Okay, so then now we hit the all or none, we hit that threshold, and now the impulse moved on. Now we're going to go back to our resting potential because we were able to pass on our neural message. So now the sodium channels are going to close and we are going to repolarize. And we said polarized is negative, depolarized is turning from negative to positive, and now we're going to repolarize and go back down to an overall negative charge. So repolarizing, it's going to fall and become negative. And then what happens is you have hyperpolarization, which is the same thing as when the absolute refractory period happens. So the absolute refractory period is when after the action potential happens, it goes back down to negative, and it's this little minimum length of time during which another action potential can't begin. So it's like a recharging phase. You have to dip down really far into the negative here, where it actually goes below what it typically is. It'll be like at like negative 80 or something like that. So it dips down really negative to a point where another action potential can't happen for like 1 to 2 seconds. So think this neural communication happens like instantly. So it's like a teeny little break in 1 to 2 seconds where it has to recharge, reboot, and you can't have another action potential pass for that teeny little period of time. Then it's going to go back up to its resting potential at negative 70. And then it can all start back up again, yay, and have another action potential and all that jazz. So that is that when it comes to neural communication. So other thing I want to write, big thing I think that we get mixed up on is with synaptic transmission. So having that message pass on to another neuron is that no neurons touch each other. The small space separating them is called the synapse, and the electrical message can't jump. So that's why it uses a chemical message called the neurotransmitter. The neurotransmitter is just the little like crossing guard that's there to help the neural impulse cross the street, cross the synapse, and get to the other neuron, the dendrites of the other neuron. And then once they go back, once you open up the door, and they're the key that opens up the door and allows you to send the message on to the next neuron, they just go back. They don't get continued sending on through the next neurons. They open up the door and then they float back to the previous terminal buttons of the neuron that was sending it. So this is a process called reuptake, which, there we go. So through reuptake, they're just recycled back up into the neuron, the terminal buttons of the neuron in which they were released from. So they don't carry on, they just go back home, and they're constantly being recycled back into that sending neuron. All right. And this is just an image of that key lock mechanism like I was saying before. So just to review, a really good way that I remember this is the toilet analogy. And what's more relevant now? Yeah, toilet paper is all we talk about these days. So neuron firing toilet analogy, here's how to remember it. So a toilet has an action potential because when you flush it, an impulse is being sent down the sewer pipe, right? Because a toilet's just chilling at resting potential. It's charged. You could flush it at any point, but it's not actually doing anything when it's just sitting there. So it has the potential to flush or send the impulse, but when it's at resting potential, it's just hanging out neutral. So then you flush it, the action potential happens, the impulse is sent, and the toilet operates on an all or none principle. It's always going to flush with the same intensity, no matter how hard you're holding down the handle or pushing it. So that's the example. It's always, if you just hit it too lightly, it might not hit the negative 55 threshold. But once you do hit it with enough force, holding it even harder or pushing it even harder isn't going to result in it flushing more intensely. And then also, a toilet has a refractory period. So it's the short period when you can't flush it. It has to recharge and refill its water tank before you can send another action potential or flush down there. So that's it. And then one last term I want to talk about related to neurons is called long-term potentiation, or also referred to as LTP. And this is a term that comes up not only in the bio unit, but also in learning and memory. And it's come up on FRQs before, so it's a really good one to know. So let's throw it back to when we did that little demo in class when we learned about the neurons, and I passed around the little sheep, and you guys acted as different parts of the neurons, dendrites, nucleosoma, etc., passing it on from one neuron to the next. So the example with the sheep, the more times that you guys passed it through and we timed it, the faster it got. And that was supposed to represent long-term potentiation, because LTP is when neurons strengthen their connections the more times that they're fired. So the more times a message gets sent or fired between neurons, the more sensitive the receiving neuron is to messages from the sending neuron, which means that there's a stronger connection and therefore better memory and learning has occurred. So it's what you'd call the biological basis of learning, because it's really just the more times you're repeating something and sending that connection, the stronger it gets and the stronger the memory and learning that has taken place. So a really good term to know, and you can just think back to our sheep demo, and we got our time faster and faster each time that we passed our little sheep neuron, our sheep neural message down the road. An easy way to remember it all. Okay, so like I said, neurotransmitters are just the things that are the little crossing guards that help you cross the synapse, and they're the keys that open up the locks on the receiving dendrites of the next neuron. So there's two types of neurotransmitters. There's excitatory and inhibitory neurotransmitters. Excitatory are ones that make a target neuron more likely to have an action potential. So it's going to keep sending on the message to the next neuron. So it's like a green light. Then other neurotransmitters are inhibitory. An inhibitory neurotransmitter makes a target neuron less likely to fire an action potential. So it's like a stop sign. It's going to stop the neural impulse from being sent on to the next neurons. So now I put together this handy dandy little graphic to try and remember the different types of neurotransmitters. I know these are tricky, and I wish we could spend more time on these in class, but we have such a short amount of time in our day to be able to do that. So here's some kind of mnemonic devices to try and help you remember the different neurotransmitters. So up first, we have glutamate. Glutamate is the primary excitatory neurotransmitter, so it's what kind of keeps those messages sending and makes them more likely to be sent. Its function is related to learning and memory mainly. And it's also related to a term called long-term potentiation. And long-term potentiation, we said, is kind of when, if you think back to our example demo in class, when we passed that sheep and tried to mimic the actions of neurons sending a message, the more times you send messages, the stronger the neural connections you're forming, and the faster you can then send the messages because you're making those stronger connections with different neural pathways. So glutamate helps with this. So it's really important in learning and memory because the stronger your neural connections are, that kind of demonstrates that learning is occurring. So glutamate, I remember that it is with learning and memory because it glues memories together and makes them solid. So glutamate glues memories. GABA is the primary inhibitory neurotransmitter. So we said inhibitory is kind of like the stop sign that slows things down. And their function has to do with anxiety reduction and relaxation because it's inhibiting, it's kind of slowing and chilling things down. So GABA, I think, this is kind of a stretch because I couldn't think of anything, but GABA, there's like that TV show for little kids called Yo Gabba Gabba. And because GABA is very related to being chill and relaxed, I said you could just think, yo, GABA Gabba. So it's very chill and relaxed. I don't know if that helps. Endorphins. And just to kind of put this all together with the abnormal psych unit, something like GABA, it's related to anxiety reduction. So if you're low on GABA, that means you could have kind of an increase in anxiety. So you'd want more GABA to try and prevent anxiety. Next thing are endorphins. So these are related to exercise. So endorphins are things that inhibit pain. So they're released when we're in pain or when we're exercising. So often they're released when we're exercising. And this is what they result in what you'd call like a runner's high, where you're feeling really good when you're running. And that's because those endorphins are being released. And a related drug would be like opiates because they're kind of reducing pain. So a way to remember endorphins, you can think one, endorphins, exercise, endorphins exercise, or you can think endorphins and pain. So end orphans, end pain. Then dopamine. I took this from the little fun things that Instagram does and screenshotted it. So dopamine is the kind of probably the most important neurotransmitter to know, in my opinion. It shows up more frequently, I think, than the others. So know this one. Dopamine is related to pleasure. It's your pleasure center and reward. So that's why kind of things with drugs with like dopamine are very addictive, because it gives you that sense of reward and pleasure. So reward, pleasure are the two main things to know. It's also tied in with things like voluntary movement, posture, learning, cognition, attention. But dopamine, you can just think it's dope. It's really good. It feels nice. People who dope probably feels good or something like that, I guess. So pleasure, reward. People who dope, you think like doping up before a bicycle race or something like that. They're trying to achieve a reward, so you can think about it that way. So hopefully that's useful. Serotonin is related to mood, appetite, sleep, and impulse control. So we talked about briefly in motivation, emotion, because it's tied in with kind of our eating patterns. So easy way to remember. And also with serotonin, we said it's related to mood. And that's why with something like depression, if you have low serotonin, that's when depression could kind of start. So you want a selective serotonin reuptake inhibitor, which is the drug that would kind of combat depression. And the serotonin reuptake inhibitors, we know reuptake is when the neurotransmitter goes back to the original sending neuron. And we want a serotonin reuptake inhibitor, because if we're inhibiting the reuptake of serotonin, it's going to result in a buildup in the receiving neuron of serotonin. So that's a good thing, because it would kind of increase the serotonin in your body. So serotonin, mood, appetite, impulse control, sleep. So serotonin, you can think S, sleep, serotonin, and then serotonin, sad, you can think it's mood, because if you don't have enough serotonin, you'll be depressed or sad. Norepinephrine, I mentioned this earlier with our fight or flight response. So norepinephrine is connected to arousal, which is clearly related to that fight or flight response, and attention. So again, connected to the sympathetic nervous system by activating fight or flight response. It's also both a neurotransmitter and a hormone, so it's unique in that. Easy way to remember that it's connected to fight or flight and arousal is you can think norepinephrine. Norepinephrine, fight or flight response, you need a arousal and you're going to run. You're going to flee. And then acetylcholine, I think this one has also popped up in an APF or a Q before. So acetylcholine has to do with muscle contraction, memory. I put that twice, so I can really know it. Memory and learning. So an example is that a drug that is an antagonist, so it's blocking acetylcholine, would kind of paralyze your muscles and make them harder to move. And that's what you see with botulinum toxin. Botulinum toxin is an antagonist of acetylcholine. And that's when someone gets Botox, it kind of freezes their skin and it makes it difficult to move and contract the muscles, making you look younger. Interesting stuff. So a way to remember that it's tied in with muscle contraction, you can think acetylcholine, muscle action, AC, muscle action. And then it's also tied in with memory. So you actually see if you are lacking acetylcholine, you could have Alzheimer's or things like that. So you can think AA, acetylcholine, Alzheimer's, memory. Okay, so now on to drugs real quick. We know that we reviewed that an agonist is kind of like a drug that is a poser. So it's kind of the kid with the fake ID who's trying to trick the bouncer to get into the club. So they are things that mimic or enhance neurotransmitters. So nicotine kind of mimics or enhances acetylcholine. So an example here is, let's see, you can't really see my picture too well, but they're not quite exactly what the neurotransmitter, like the shape and form, but it looks enough like the neurotransmitter that it's gonna kind of fit into the lock and still kind of set it off. So it's kind of like a fake ID. That's kind of the lock that isn't quite exactly what it is, but it's still working enough to fit in and kind of mimic or enhance that response. An antagonist, you can think anti, it's going to block. Antagonist, anti, is the blocker. So if you put your key in your apartment door, but it doesn't fit, and then you like try it so hard that you just break it off and now it's stuck in there, and then no one else can get in. So it's going to turn down the effect of a neurotransmitter and kind of block it. So that's why I said botulinum toxin and acetylcholine. It's kind of blocking it from working. Here's my picture. So you can see, again, here's an agonist. So it's like not quite the neurotransmitter, but it kind of sneaks in and fits to kind of enhance the effect of the neurotransmitter or mimic it. Then the antagonist doesn't fit and it just kind of ruins it and blocks it. So other things can't get in and kind of decreases the effect of the original neurotransmitter. And then to end, we have the psychoactive drug categories. So we have depressants. These are things that decrease central nervous system activity and kind of slow things down. So your breathing, heart rate decreasing. Things like alcohol, opiates, anti-anxiety meds. Stimulants stimulate our central nervous system, so turn things up. So breathing, heart rate, those are increasing. Things like caffeine, nicotine, cocaine, amphetamines, MDMA, ecstasy, hallucinogens. These are things that result in disordered sensations and perceptions, right? So anything that's kind of resulting in, seeing things, hearing things, an altered sense of reality. That would be like marijuana, LSD, and things like that. So that was a lot. Whew. But a good review. Again, I'd probably say the best thing, because I know we didn't spend too much time on these, are kind of thinking of the mnemonic devices for the neurotransmitters. And then neurons some of it could be on there, so it's still good to know and review a little bit. And then best thing would be to kind of look back at this breakdown of the nervous system, because these show up on the AP exam a lot. So knowing kind of especially fight or flight response. So all this stuff, know what motor neurons are, somatic, just know it all. So put it together and review those. That's probably the best thing that you can do. All right, keep up the good work. Have a nice day, you guys.